Hey there. I want to continue our study of parametric curves, and the next thing I want to talk about is arc length. Now, so let's recall, right? If we have a curve in the plane with parametric equations, so let's say if C has parametric equations, x equals f of t, y equals g of t on some interval like that. And of course we need the curve to be traversed exactly one time, so but just remember that. So if we have this, then the length is, and it's typically written as little s, it's equal to the length, the integral from a to b square root f prime of t squared plus g prime of t squared dt, right? So we learned this when we were studying parametric curves in the plane. Now, it turns out then, if we have a curve in 3 dimensions, then the same formula holds. We just have an extra coordinate here, or component here, which will give us an added piece in our integrand. So if C has parametrization, and I'm going to write this in vector form, so R of t equals f of t, comma, g of t, comma, h of t, then the length of the curve is going to be the integral. And I need to give a range here also. A less than or equal to t less than or equal to b. Then the length is equal to the integral from a to b. Then we'll have a big square root here with an f prime of t squared plus g prime of t squared plus h prime of t squared dt. So it's essentially the same formula, we just have one more component, and this will compute the length of some curve, right? Oh, that was kind of sloppy. Some curve now in 3 dimensions. One thing to notice here, in both cases, right, especially if I wrote this in vector form, right, you don't need to write this down, but we could, of course, for 2-dimensional curves, we could write it in vector form now, like that, f of t, g of t. And so now my question is, when you look at the integrand of this one and this one, it should look familiar. And what it is, right? When you see a square root, you should think length. We're adding the squares of components. This is distance in either 3 dimensions or 2 dimensions. And so what this is, it is, right? So let me write this down. So note that the length of r prime of t is equal to the square root of f prime of t squared plus g prime of t squared if it's in 3 dimensions. And so let me let's do it like this. So h prime of t squared, where this part you need for 3D. And so we can now, this gives us a compact form. So in compact form, the length of a curve is equal to the integral from a to b, and then your integrand is the length of the velocity vector, right, of the derivative. And so that is a nice way to remember what the, to remember the arc length. so let's try an example. So let's find the length of one revolution of the helix. Remember, the helix was that spiral shape. So one revolution of the helix, which I'll write in vector form r of t, equals cosine of t, comma, sine of t, comma, t. Now, if we want to do one revolution, right, so remember, right, the helix goes around the cylinder, and so one revolution means go one time around. Let's say from here, go around to here. And so that corresponds to theta or t going from 0 to 2 pi or 2 pi to 4 pi, any increment of 2 pi. And so I'm going to compute the one that goes from, right, this corresponds to t equals 0. This one corresponds to 2 pi. Okay, so now what we need is r prime of t. All right, to do that, you just compute the derivative. So minus sine t, cosine t, 1. And then the length of r prime, right? So that's going to be square root minus sine quantity squared, so that'll be a sine squared, plus cosine squared t, plus 1. Now, noticing that this is equal to 1, what we get is that this is going to be square root of 2. And so, the length is going to be the integral from 0 to 2 pi square root of 2 dt, and so that will be square root of 2 times t, go from 0 to 2 pi. That's equal to, well, root 2 times 2 pi. One thing to be aware of, right, anytime if you're computing arc length that involves a square root in the integrand, that can make life difficult. And so the problems have to be rigged, right? When you see the ones in the book, they'll be rigged so that you can actually compute the integral. So let's say that we have some curve given by a parameterization. So if we are given a curve with parameterization, r of t on the interval from A to B, I want to define, so we define the arc length function. And now we're going to write it, think of it as a function whose variable is t, and so it's going to be s of t, and it's equal to the integral from A to t of, now I need to use a different variable here, so I'll use r prime of u, absolute value, du. Now, what this does, all right, so let's draw a picture here. If I have a curve, right here is r of a. Well, okay, officially, right, we've got the position vector pointing there. And then r of b would be a position vector that comes and points right to there. I'm just going to mark the ending point there. So there's r of b. Now, what this function does then is says, okay, tell me a value t, and when you do, there will be a corresponding point on the graph. And so the arc length function measures the length of the curve, right, from the beginning to that point r of t. right? So so S of t measures the length of a portion of the curve from R of A to R of t. And you can change t, so right, so if you choose t to give you this point, fine, it tells you this length. If you choose t to give here, then it'll measure the entire portion of the curve from here to here. All right, so you can, as t varies, you get different answers. Now, if you apply the fundamental theorem of calculus, I'd like to take the derivative. So, so by the fundamental theorem of calculus, right, the derivative, so this would be ds dt, is equal to the length of the velocity vector, or length of the derivative. Now, I briefly said something about smooth curves, so now I want to make this precise. So let's put this in a little box. So now we need a definition, a parameterization. R of t is smooth, so I think I mentioned this in the last lecture, on, well, I guess I gotta say on the interval from A to B, if R prime of t, so we need to be continuous, so is continuous, and R prime of t not equal to 0, right? So in this case, we call it a smooth parameterization, right? We need this derivative function to be continuous and the derivative never equal to 0. And in this case, it's the 0 vector. If a curve has a smooth parameterization, then we say that the curve is smooth. So if C has a smooth parameterization, then C is smooth. And so here's the idea, right? I mean, something like this, right? A sharp point on your curve, that's a spot where the curve is not smooth. Right? And what you have is an abrupt change in, say, the tangent vector there. Right? Discontinuous. Yeah, so for example, let's look at this one here. R of t equals cosine of t, comma, t squared, comma, t cubed plus 1. So let's look at r prime of t. That's going to be a minus sine t, 2t, 3t squared. This is continuous, right? Each of these component functions is continuous. But, so note, or let's say since r prime of 0, that's going to give us the 0 vector. R of t is not a smooth parameterization. Okay, so there's our idea of smoothness, right? And it fits exactly with what you would think, right? You want to think that as you travel along this curve, there's no sharp points. And also, when it says r prime of t is equal to 0, what does that correspond to? That corresponds to stopping and then starting again, right? So that's another, it'd be a sort of non-smooth way of traveling along the curve. Okay, now what I'd like to do, write that a little better, I want to study curvature, right? So when we have a curve, right, you don't need to write this down. There are some times when you're traveling along the curve, you're going relatively straight, right? In some places, maybe you're going very straight, right? Or a little bit, maybe there's a little bit of a turn, But notice in this area, right, if you're traveling in a car along this path right here, or whatever, if you're traveling along this pathway, right, you would notice that you're turning, right? You would feel the turn, right? Where here in this gradual turn, you would feel it much less. And so what we want to do next is characterize what it means to have to turn in tightly, to have tight curvature, or flatness, right? Non-turning, non-curved, right? So we want to characterize how a curve curves. And here's the idea. What does it mean to curve versus not curve? Well, what we want to do is look at the unit tangent vector. And so I'm going to pick a few spots on this curve here, and I'm going to draw, in each case I'm drawing the unit tangent vector, so it has length 1 in each case. Okay. So in each of these cases, right, pick a value t, and then what we're looking at is, remember the unit tangent vector, that is r prime divided by the length of r prime. And so here's what it means. What we want to do is capture what it means to curve a little bit or a lot as we travel along our curve. And notice, in these places where it's relatively straight, the unit tangent vector is essentially the same. There's almost no change in the unit tangent vector, right? It's still pointing in almost exactly the same direction. However, as we start to go around the curve, when we change even a little bit, as we travel a little bit, right, the direction of the unit tangent vector changes a lot, right? So notice from here to here, the direction of the unit tangent vector is nearly the same, very little change over this amount of arc length. However, if we did the same amount of arc length, let's say it's about this much, right? Notice the unit tangent vector, and I'm halfway out of my shot right now, but the unit tangent vector is pointing up and then is pointing down. There's a large change in the direction of the unit tangent vector as we go around that curve. Same thing here, right? By making just a little bit, just a small amount of travel along the arc length, right? And there's a humongous difference in the direction of that tangent vector. So what we'd like to do is we'd like to capture that in a single quantity, right? We want to measure the curvature. And so let me just sort of say this. So when C curves a little, the unit tangent vector changes slowly. When C curves a lot, the unit tangent vector changes quickly. So what we want to do then is measure the change in the tangent vector, and so we can do that. Okay, so here's the definition. The curvature of C is, and it's usually written as, in your book, it's a little kappa, which is kind of like a little k. And so by definition, the curvature is all right, so let's look at this. This is the change in t with respect to the change in arc length. Okay, so this quantity right here, that's called the curvature. Now, I just want to throw out, so this is the chain rule. We're never going to use this formula right here. We're going to find a better formula for computing curvature. Right? But this curvature, you want to interpret this as a number that quantifies how the curve is curving at a particular instant. Right? At this moment right here, it's changing a lot. At this moment over here, it's changing very little. Right? So, okay, so what we want to do is develop a way to think about this, or computationally. So according to the chain rule, dt d little t, that's equal to d t ds ds dt. So if I solve for dt ds and take the magnitude, we can say so. The curvature, which is absolute value, not absolute value, magnitude, dt ds is equal to, so that'll be the derivative, or the magnitude of the derivative of the unit tangent vector divided by ds dt. That's the derivative of the arc length function right there. And so, let me put this as a theorem. So this is going to be a formula that we will use to compute. So this is a theorem. If C has smooth parameterization R of t, then the curvature at t is little k equals magnitude of t prime of t divided by arc length, or the length of the velocity vector. Okay, so there's an actual formula that we could use to compute curvature. Okay, so let's try an example now. So let's find the curvature of the curve C given by parameterization R of t equals t squared t. This is a smooth parameterization. We're not going to verify that. At the point 0, 0, 0. Okay, so let's see what we need here. We're going to need the derivative of the unit tangent vector, and then we're going to divide that by the derivative of the position vector. So we're going to need some derivatives here. So r prime of t is equal to 1, 2t1. We need the length of rt, so the length of r prime of t is going to be the square root of 1 plus 4t squared plus 1. That's really 1 squared plus 4t squared plus 1. So that gives us square root of 2 plus 4t squared. Okay, so this is going to be our denominator when we compute the curvature. So now remember, the unit tangent vector, that's going to be r prime divided by the length. And so capital T of t is equal to 1 over square root 2 plus 4t squared times 1, 2, what am I doing? Yeah, 1, 2t, 1. And now I need to take the derivative. So t prime of t is equal to, and here, there's two different ways to do this. What I could do is I could bring this constant, if you like, this scalar inside each of those and then take 3 derivatives separately. Or it turns out you can also just use the product rule. This times the derivative of this plus the derivative of this times this. That's what I'm going to do. So and you can look in your book, there actually is a formula that tells you that the product rule works. So it's going to be this function times the derivative of the vector, which is 0, 2, 0, plus, now I need the derivative of this function, that's going to be a minus 1/2, 2 plus 4t squared to the minus 1/2 times 8t, which will give me minus 4t over, oh shoot, no, that's already in the minus. Sorry. Yeah. So it's good. This is already. Sorry, I started to write that wrong. So that's already a minus 1/2. So it'll be a minus 1/2, 2 plus 4t squared to the minus 3/2 times 8t. So that's going to be minus 4t divided by 2 plus 4t squared to the 3/2 times the vector 1, 2t, comma 1. Okay, so now we want the curvature at the point 0, 0, 0, which corresponds to when t equals 0. So t prime of 0 is equal to, so I'm going to plug in a 0 here. This is going to give me a 1 over root 2 times the vector 0, 2, 0, plus, actually minus, oh, actually this gives me a 0, so that's gone. Right? So it comes out to be the vector 0, 0, 2 over root 2 and 0. Which means then that the magnitude of t prime is equal to 2 over root 2 squared, add them together, yeah, so 2 over root 2. Okay, so this, sorry, this is, I don't want a t there, I want a 0 there, right? Because now we're computing it at 0. So this is the magnitude of the derivative of the unit tangent vector at t equals 0. I also need to plug 0 into this piece right here. So the magnitude, well, yeah, let me do it over here. We'll say also. Oh, let's rationalize this. Why am I being so cryptic here? So times root 2 times root 2. That cancels out the 2, so this is just square root of 2. And then we can say also the magnitude of r prime of 0. Okay, so if I plug 0 in here, I'm going to get square root of 2. So what's our conclusion? The curvature at 0 is equal to, so it's going to be, let me write out the formula here, t prime of 0 magnitude divided by r prime of 0 magnitude. That is going to be root 2 divided by root 2, which equals 0. So, which equals not 0, equals 1. All right, so the curvature at 0 is equal to 1. Let's try another example. Let's find the curvature of the circle of radius little a. Okay, so remember we can parameterize a circle. So r prime of t equals, I'm going to write it in vector form rather than in parametric form. R of t is equal to a cosine t, comma b a sine t. Right? If it is an ellipse, there'd be an a and a b. Okay, so I want to compute the curvature, so I need some derivatives now. So r prime of t is equal to negative a sine t, a cosine t. The magnitude that's going to equal square root of a squared sine squared t plus a squared cosine squared t. If you factor an a squared out of each piece, then you'll have sine squared plus cosine squared, which is 1. So we'll have a squared under the square root. So that's equal to a. We also need... okay, so that tells us that t of t is equal to well, okay, so it's going to be 1 over a times r prime, which is minus a sine t, comma a cosine t. Right, t prime, that's the unit tangent vector, so it's r prime divided by the length of r prime. And so this simplifies to be negative sine t, comma cosine t. Now we need t prime, right? We need the derivative. And so that'll be a minus cosine t, comma minus sine t. So next step, we need t prime. Oh, actually, I'm going to leave it as t prime. Sorry, t prime of t magnitude. That's going to equal. Well, the magnitude of this is going to be a cosine squared t plus sine squared t under the square root. That equals 1. And so the curvature, that's going to be the magnitude of t prime divided by magnitude of r prime. And so that's going to be 1 over a. Now remember here, we are finding the curvature of a circle of radius a. So let me draw a couple of different circles, right? So here's a kind of a big circle. If that's our a, right? If a is large, then what happens to our curvature? Our curvature is small. If a is tiny, if you to make a tiny little circle there, right? If a is small, then the curvature is large, right? So this should make sense, right? If you're going around a really big circle, in fact, if this was gigantic, then you might hardly even be able to tell that you're curving, right? As you travel around the circle. But on a real tight circle, you would expect the curvature to be very high, right? So this formula hopefully makes sense. Now, one thing to notice, computing curvature is kind of a pain, right? Because you got to compute capital T prime, right? And that just creates, it can be kind of a mess. And so it turns out that there's a formula that simplifies the computation. So computing curvature can be simplified by the following formula. So the curvature at t is equal to the magnitude of r prime of t cross r double prime of t divided by the magnitude of r prime of t cubed. So this will accomplish exactly the same thing as our previous formula, right? The one involving the unit tangent vector. And so there are definitely times when I'm going to opt for this. In fact, always, essentially always, I'm going to opt for this formula right here when it comes to computing curvature. So what I want to do is let's repeat the previous example, right? That was the one where we computed the curvature of, what was it, r of t equals, so r of t equals t, was it t squared, and then t. Okay, so I want to compute the curvature at t equals 0, right, for this curve right here, or the parameterization of this curve. So r prime of t is going to be 1, 2t, 1. R double prime of t is going to be 0, 2, 0. R prime of t cross r double prime of t. That's going to be 2, 0, and 2. The magnitude of r prime of t cross r prime or r double prime of t is going to be the square root of 4 plus 4, so that's the square root of 8. The magnitude of r prime of t, that's equal to square root, remember this was 2 plus 4t squared. So at 0, so let's now say who the curvature is at 0 using this formula right here. So the curvature at 0 is going to be square root of 8, that's this evaluated at 8, divided by, let me write it out. So so it's going to be magnitude r prime of 0 cross r prime or r double prime of 0, which means just plug zeros in here, which there's no variable here, so it just gives us the square root of 8, divided by magnitude of r prime of t cubed, r prime of 0 cubed, and r prime of 0 is going to be square root of 2 cubed. So what do we get? We get square root of 8 divided by square root of 2 cubed, which is exactly square root of 8. Right, so we get 1. Right. So I think this computation definitely simplifies things, right? And so when I need to compute curvature, this is typically the formula that I'm going to opt for. Now, there's one special case. What we've been doing is studying parameterized curves. So special case. If C is the graph y equals f of x in the plane, then the curvature has an even easier formula. It is absolute value of f double prime. I need to say then the curvature at x. So k of x is equal to f double prime of x divided by 1 plus f prime of x squared, all raised to the 3/2. So here's the idea now. We have this general formula, these general formulas that allow us to compute it. If you have some curve now, let's draw a better looking graph. That was much better. So if we have some point x comma f of x, right, on the graph y equals f of x, right, then you can compute the curvature using this formula right here. So let's try a quick example. Let's find the curvature of the graph y equals x cubed at x equals 1. All right, so all we need to do is take a couple of derivatives, throw it into this formula right here, right? And our picture looks like this, right? We're looking at the graph of x cubed at x equals 1, so we'd like to know the curvature there. Okay, so the curvature, well, let's compute derivatives first. So f of x equals x cubed, f prime of x, 3x squared, f double prime of x is 6x. And so we need, so the curvature at x is going to be 6x absolute value divided by, well, that's 3/2. 1 plus 3x squared squared. So that's going to be 6x to the 4th raised to the 3/2. Okay, so now we want the curvature at 1, so k of 1, that's going to be a 6 in the numerator and a 1 plus 6, so 7 raised to the 3/2. So there's the, it's not a nice number, but there's the curvature at that point right there. Yeah, okay, so that's a good place to stop. So we'll see you next time, okay? Hey, sorry, I just realized I screwed up right here when I squared this. This should actually be, so I'm plugging in the derivative, that should actually be 9x to the 4th. And so what you get here, when you plug in a 1, it's going to be 1 plus 9 raised to the 3/2, so it'll be a 10 to the 3/2. Whoops, sorry about that. Fix that in your nose.